Geometry class, this is section 9.5. It is just tangent lines. Tangents, you probably have heard this word before when we've done like sine, cosine, and tangent. Okay, but tangent in this context is different than this tangent, so not quite the same. When we start to get into calculus, for those of you who will take calculus like your senior year, there is sort of a correlation between the two, but that's not, they're not quite the same today, what we're talking about. Tangents in this section have to do with tangent lines. So a line that's tangent, let's say you have a circle. A tangent line, if you would pick a point on that circle, is a line that will touch that point at just one place, okay? If you think of it like a bike tire or like a yo-yo, here's what a yo-yo would look like, okay? Imagine that string coming down off of the yo-yo. It's going to touch the yo-yo at one place before it wraps around the yo-yo. Okay, that's what the string will look like. This line right here is tangent. It kind of forms a T in relationship to your object, in relationship to your circle. When we get into calculus, we have curves. So we're not talking about circles, we're talking about just curvy lines, and we're doing tangent lines to that curve. So just a line that's going to touch a curve or a circle at just one place before it kind of veers off in the other direction. Okay, so that's what a tangent line is. It kind of makes a T with your object. Okay. All right, so tangent line intersect a circle at exactly one point. The place where it crosses or it intersects is called the point of tangency. If you can see that on your sheet, it's also here. Point of tangency is that place where he's crossing or touching at one point. Whoop, I need to make this bigger, sorry. Okay, when you have two circles that are going on at the same time, you can draw what's called a common tangent, which is a line that kind of intersects both of them at the same time, or is tangent to both of the circles. So this guy's touching here at one place and here at one place. And if you imagine this is like a bike, where you have two different sizes of tires, it kind of looks like a wheelchair almost even, because the bigger wheel is at the back and the smaller wheel is at the front. Imagine that you have like a gear going in between them, or like, I don't know, on a bike it has whatever this thing is. That gear in between them, what? Frame? Yeah, kind of, I guess. There's like a gear going between the two tires that kind of rotates the tires around, okay? That's kind of what the tangent line goes off of. So we have this little gear going in, or that line going in between them, that's going to touch those circles at just one place, okay? When the circles are butt right up against each other, this tangent line is just going to go straight up and down vertical, where it's touching those two places at exactly one point, okay? A and B are kind of fun. I don't think your homework assignment has any that are like this, but they want us to draw tangent lines. If there is no tangent line, you put no common tangents, but A and B both have at least one tangent line. If we're trying to draw a tangent line, a line that touches both of those circles at just one place, it would go kind of something like this. Okay? He's touching right here at one spot and touching right here at one spot. Okay? Now, if you think about that being one place, and then there's also a place here at the bottom that's going to touch there at one spot and touch there at one spot. So you actually have two common tangent lines that are touching both of those circles at just exactly one spot. Okay. B kind of looks like this problem up above here. So I know that there's a tangent line that exists right here that's touching at just one spot there and just one spot there. There's also one going this opposite direction. Pulley system. That's what I was. That's the word that I was thinking of. It's like two gears and like a pulley system. Okay. So there's those two lines, but there's actually two more on top of that. Okay. There's the ones that go this direction. I'm trying my best to draw straight lines here. He's touching there at one spot, there at one spot, and then you can see the ones on the bottom also. Okay. There at one spot, there at one spot. So there's four tangent lines, four common tangent lines in part B. Okay, they're kind of like gears going around those, or pulleys going around those gears. Okay, all right. Theorem 910. There's two theorems in this section. Theorem 910 says that if I have a circle and I have a line that's tangent to that circle, meaning that it's only touching at one point, If I draw the radius from the center to that point, that radius has to be perpendicular to my tangent line, always. It forms like an upside down T, T for tangent. Okay, so in that theorem I went ahead and wrote on the theorem sheet, theorem 910, a line tangent to a circle is perpendicular with the radius. A line tangent to a circle is perpendicular with the radius. Okay, I went ahead and draw my circle. Here's a tangent line. Mine looks a little bit different than the one that's on your homework sheet, but if you want to draw that one, you're more than welcome to. This one's off at a slant over here, and my radius is connecting that, and it makes a 90-degree angle. So a line tangent to a circle is perpendicular with the radius. Line tangent to a circle is perpendicular with the radius. That's theorem 910. Okay? All right. So example 2, where we are trying to determine, it says JL is a radius. This guy right here is a radius. We're trying to determine whether KL, whether or not that is a line that's tangent. Now, from the theorem that we just had, if this line is perfectly tangent to this circle, this will be a 90-degree angle. Okay? Well, they've drawn kind of a right triangle there for us. So basically what we're trying to determine is if this is a right triangle or not. Okay? If it is a right triangle, if those numbers match up in the Pythagorean theorem as being a right triangle, then we do know that this line is tangent, okay? Now this gets kind of confusing. This 9 right here is in between these 2 points. 9 is like kind of in the center here, so 9 is just the distance from here to here. Okay, it's not the length from K to all the way to J. This point to J is actually 8 because 8 is there, and that's another radius, so this entire length is 17. So now we're looking at a triangle that has lengths 15, 8, and 17. We're going to try and see if that is a perfect right triangle. So 15 squared plus 8 squared has to be 17 squared. 15 squared is 225, 8 squared is 64, 17 squared is 289. So we're seeing if these two added together make 289. 225 plus 64, yep. 289 equals 289. So that means that this is a right triangle. This is the right angle in that right triangle. And then that means this side or this line has to be a line that's tangent, because if it's a if it makes a 90-degree angle, this line has to be tangent to the radius, okay, or tangent to the circle, right? So yes, KL is a tangent line. KL is a tangent line. Okay? All right. Example 3, we're finding missing values, so they have x's and stuff in here, and it says that JH is tangent to circle G. So this guy right here is a tangent line. GJ is my radius, and from the theorem up above, we know that if that occurs, if that's a tangent line, this has to be a right angle. So we're going to use the Pythagorean theorem again, where my sides are 12x, and then this long side here is actually x plus 8, okay? It's not 8x, it's x plus 8. Those are those lengths together, all right? So we're going to do the Pythagorean theorem. I have x squared plus 12 squared has to be equal to x plus 8 squared. X plus 8 squared. Okay, now, I see people do this all the time. When you have x plus 8 squared, write this on your notes. X plus 8 squared is not equal to x squared plus 64. That would be really, really, really nice if it was, but it is not. X plus 8 squared actually means x plus 8 times x plus 8. Okay, if you took Algebra 2 with me, you'd know that I harp at you all the time about that. Okay, so what we have to do here is we have to actually have to FOIL. So we would take x times x first to make x squared, then x times 8 makes plus 8x, then 8 times x is another plus 8x, and now 8 times 8, that's where the 64 comes in. Okay? So if I put this all together, all 4 of those pieces together, I can put the 8 x's in the middle together. So x squared plus 16x plus 64. This is a lot different than x squared plus 64. It's got that 16x in the middle. Okay? You can't forget him. All right? So we've got on this side, we've got x squared plus 12 squared is 144. And then I'm going to write off to the right side over here what x plus 8 is, or x plus 8 squared. We have x squared plus 16x plus 64. Okay, this kind of looks tedious, but we are really almost done. This actually does come out very, very nicely. Okay, so what I see from this equation here is that x squared and x squared, those two I want to kind of join together. So I'm going to move this x squared onto the other side, and I can only do that by subtracting an x squared. So minus x squared minus x squared. I cross those two out. That's kind of nice. I like it when x squared crosses out, because then I don't have to deal with square rooting or doing anything like that. Right? So I've got 144 equals 16x plus 64. And all I have to do is solve for x. So I'm going to bump this 64 to the other side. I'm going to subtract 64. So I've got 80 equals 16x. And then I just divide by 16. Yeah, ran out of room. 80 divided by 16 actually does come out really nicely. It is 5. Okay, so it was kind of a lot of work, but it does come out really, really nice in the end. And with those x squareds canceling out, that makes it really, really super nice. Find the value of x. We did that. We don't have to plug back in or anything, so x is 5. All right? Okay, moving on to the back side. We have one more theorem, and this is one of my favorite things to teach ever. It's awesome, because you'll never forget it after I teach it to you. Okay, Theorem 911. We have two lines that are tangent to the circle. So tangent is where it touches at one point and it veers off in the other direction. It's touching here at one point at C and veering off the other direction. Okay. When I have two tangent lines that are intersecting with one another, kind of like these do, those two tangent lines are exactly the same size. Okay, I'm putting little tick marks there to show that they're exactly the same length. So if this has a length of 10, this one has to be a length of 10. Okay. The way that you remember this is it kind of looks like an ice cream cone. All right. So I have my ball of ice cream up here, and I have my ice cream cone. And if my ice cream cone was lopsided, meaning one side was longer than the other, guess what's going to happen to my ice cream? He's going to fall off. So both sides of my ice cream cone have to be exactly the same size. Now, I've had people argue with me before that like a waffle cone doesn't have both sides the same. For the waffle cone, one of them is kind of stuck up higher, like more in this pattern. And my answer to that argument is that in a waffle cone, your ice cream does not actually sit on top of the waffle cone. It's actually down inside of the cone, okay? Or it's stuck to some other ice cream that's on top, all right? So that's what's holding that in the center of the ice cream cone is other ice cream that's already down in the middle here, okay? So in a normal ice cream cone, your sides of your ice cream cone have to be exactly the same size or it falls off onto the cement and you cry. Okay? So over here, when we do that, well, let's write that one down first. Here is my theorem. Theorem 911. And my meaning to this is kind of uneducated sounding. When making an ice cream cone with tangent lines, the tangent lines are equal. So here's my ice cream cone, there's my tangent lines. Those have to be exactly the same size. When making an ice cream cone with tangent lines, the tangent lines are equal to each other. When making an ice cream cone with tangent lines, the tangent lines are equal. Okay, you can draw your ice cream cone however you want. I did this one sideways because it gives me the most room. So if you want to go over here to the side and draw a right side up ice cream cone, you are more than welcome to do that. You might have to turn your paper to actually be able to draw the ice cream cone. Do a circle and then the tangent lines off of it. Okay, all right, let's go back to the question that it asks. So in example 4, it says A, B, and C, D are tangent to D, to circle D. So A, B, and C, CB, those are my tangent lines. If they do not tell me that they are tangent lines, we do not know that they are equal. They have to tell me that those are tangent lines in order for those two sides to be equal to each other. So those are my ice cream cone sides. We can just set x plus 15 equal to 2x minus 5. So I'm going to subtract x from here to the other side. So I have 15 equals x minus 5, and then I add 5. So x is 20. Find the value of x, and we're done. Okay, that was a pretty easy one. Set them equal to each other. They're two sides of the ice cream cone. They are equal. Okay. Then it starts talking about circumscribed polygons. So you have a circle inside of like a triangle, a circle inside of a quadrilateral. This is a, what, pentagon, hexagon, okay? And when that happens, kind of imagine that like for this triangle, you have 3 ice cream cones. So here's my ice cream, there's a cone, here's an ice cream cone, here's an ice cream cone. This one has 4 ice cream cones, one there, that's a really tiny one. I wouldn't want to hold my ice cream with that little tiny cone. There's an ice cream cone, and there's an ice cream cone. This one's going to have like 6 different ice cream cones, okay? So when you're going around a circumscribed polygon, just remember that each side of the ice cream cone have to measure exactly the same. These are the same, those 2 are the same, these 2 are the same, okay? And same for that one and this one, okay? All the way around the polygon, your ice cream cones have to be exactly the same size. They give you some non-examples of polygons that are circumscribed. So this one is not because he's not completely inside of the other polygon. This one is, the circle is inside of the rectangle, but in order to be circumscribed, the edges have to touch each other. So like our tangent lines, like this is a tangent line because he's touching there. This guy's a tangent line, he's touching there. This guy's a tangent line, he's touching there at one spot. But this fourth side of this rectangle is not touching my circle at all. So he is not a tangent line, and this is not circumscribed. Okay, this one is not, the circle is not touching inside, or not touching the polygon at all. This is concentric. If you remember when we talked about concentric circles, this circle is concentric. It's like inside of that hexagon. Okay, it's kind of a vocabulary word that we haven't had in a while. So example 5, a graphic designer is giving directions to create a larger version of the triangular logo shown. They want us to find the perimeter of ABC. Okay, so going around, I see that like this length here is 8. Okay, if I look at that as an ice cream cone, this is kind of upside down. Here's my ice cream. If that's 8, then AE has to also be 8. Okay, now I look here and I see that this is 7. So that means this side of my ice cream cone has to also be 7. 7. But they tell me this whole length here is 10. The whole length from here to here is 10, and if this is 7, then this must be 3. But then I have an ice cream cone on this edge, so that's 3. So if I look at my, like, 3 different ice cream cones here, this is 8 and 8, this is 7 and 7, and this is 3 and 3. All of the ice cream cone sides have to match up with each other. And they want the perimeter. Perimeter means all of the edges. So 8 plus 7, that makes this entire side 15. 3 and 7, that makes this entire side 10, which I already knew. And 3 and 8 makes this entire side 11. So if I'm finding perimeter, I add 11, 15, and 10 together. And that is 36. 36 feet. 36 feet. Okay? I don't think they will be this mean to you, but make sure that your dimensions are all in feet when you go to add the perimeters together. Otherwise, you're going to be kind of messed up. If one of them is in inches and the other one is in feet, you're going to need to make sure that all your dimensions are the same. So 36 feet, all your ice cream cones have the exact same measure on each one of the sides. There you go.